In this video, we're going to talk about vector and parametric equations of a plane. We know that a point on a line and a direction vector define a line in R3. We also know that two non-zero non-collinear vectors span a plane in R3. So putting those two concepts together lets us know that two non-zero non-collinear vectors and a point will define a plane in R3. So that's pretty important there at the bottom. That's why it's written in red. So let's state vector and parametric equations of a plane in R3 that contain the point 8, -1, 4 and the direction vectors shown. Well, since the point 8, -1, 4 is on the plane, that means the vector 8, -1, 4 can be a position vector for the plane. Okay. And since the direction vectors 3, -9, 4 and 0, 1, -2 are not collinear, we can use them as direction vectors for the plane. And so we can simply say the vector equation of the plane is given by our position vector plus a parameter times our first direction vector, our position vector, plus a parameter times our first direction vector, and a different parameter times our second direction vector. And like it says here, we use different parameters for the two different direction vectors because a particular point on the plane may be associated with different parameter values for s and for t. And then the parametric equations for the plane are just like they, analogous to how they were before. The x will be equal to 8 plus s times 3 plus t times 0. And the y will be equal to -1 plus s times -9 plus t times 1. And the z will be equal to 4 plus s times 4 plus t times -2. Okay, and of course s and t should be stated to be elements of the reals. Now, for our next question, if we're given this vector equation of a plane and these parametric equations of a plane, let's state three other points on the plane. Well, all we're going to do is come up with three different pairs of values for s and for t. So for the first point, imagine we let s equal -2 and t equal 3. We're just going to evaluate x, y, and z and call that a point. So if we do that, if we let s equal -2 and t equal 3, 8 plus 3s is 2, -1 minus 9s plus t is 20, and 4 plus 4s minus 2t is -10. And so one of our points on the plane is 220, -10. Now we'll say, okay, let's let s be 5 and t be 0. That's a fine enough pairing. And if we do that, then 8 plus 3s will be 23, and -1 minus 9s plus t will be -46, and 4 plus 4s minus 2t will be -24. And so a point on the plane will be 23, -46, -24. And then finally, let's get crazy. We'll let s be -11 and t be +38. And if we do that, then x being 8 plus 3s will be -25. Y being -1 minus 9s plus t will be 136. And z being 4 plus 4s minus 2t will be -116. And we'll have a point on the plane shown there. And so we can say 3 points on the plane are the 3 points that we just discussed. But of course, a plane has an infinite number of points, so there'd be an endless number of solutions to this. Now, suppose we give you a vector equation of a plane as shown with the parametric equations as shown, and we want to know whether the point 31, 16, 5 is on the plane. Well, what we're going to do is we're going to let x equal 31. And so letting x equal 31 would mean that 31 is equal to 9 plus 8s plus 2t. A little bit of simplifying lets us know that 22 is equal to 8s plus t. And then we'll let y equal 16, which would imply that 16 is 2 plus 5s plus t, which would mean 14 is 5s plus t. And so rearranging equation 2, we'd get that t is equal to 14 minus 5s. And we could then take that and plug it into equation 1. When we do that, we would get that 22 ultimately is equal to 8s plus 2t minus 10s, meaning 2s is 6, or in other words, s is 3. Then we're going to be able to solve for t, now that we know that s is 3. Earlier we said t would be 14 minus 5s, so that would mean t is negative 1. So what we've done now is we've solved for s and for t, what we get when we let x be 31 and y be 16. But we're not done. What we now have to do is determine if a z value of 5 results when s is 3 and t is negative 1. So we plug it in, we let s be 3 and t be negative 1 in the parametric expression for z, and we see that we get a z value of 5, and that's what we wanted it to be if we wanted that point to be on the plane. And so as a result, we see that that point is on the plane, and specifically the point 31, 16, 5 is the point you get when s is 3 and t is negative 1. Now suppose we're given a plane with the vector equation shown and the parametric equations shown, and we want to determine whether the point 11, 2, 3 is on the plane. So we have a feeling how this is going to go. We're going to let 11 equal 1 plus 3s plus 4t. We're going to let 2 equal 5 minus 4s plus 5t. Presumably we'll solve for s and t, and then we'll test in z with those values of s and t and see if we get a value of 3. So letting x equal positive 11 means that ultimately 10 equals 3s plus 4t. Letting y equal 2, and again that's x is 11 and y is 2. Letting y be 2 means that 2 is equal to 5 minus 4s plus 5t, right here. And ultimately that means negative 3 is equal to negative 4s plus 5t. So at the bottom there we've got two equations with two unknowns. We're going to multiply equation 1 by 4 and equation 2 by 3 to help us use the process of elimination. So when we do that, we get what you see in front of us here. Now, if we add these two equations, we'll eliminate the s's. So what we end up with when you do that is 40 plus negative 9 is 31, 12s plus negative 12s is 0, 16t plus 15t is 31t. So if 31 equals 31t, that means t is equal to 1. So now that we know t is equal to 1, we sub that into either equation 1 or equation 2 from earlier to find out what s equals. And when we do that, we ultimately get that s is equal to 2. So we have s equals 2 and t equals 1. What we're going to do now is see when s equals 2 and t equals 1 if this expression for z equals 3. So does 3 equal negative 3 plus 6 times 2 minus 8 times 1? And the answer is no. Negative 6 does not equal negative 8. So therefore the point 11, 2, 3 is not on the plane. So in summary, to determine whether a given point is on a given plane when the plane is written in vector form or parametric form, we need to get the plane into parametric form. Then we set the x-coordinate of the point in question equal to the parametric expression for x, and the y-coordinate of the point in question equal to the parametric expression for y. Then we usually use substitution or elimination to solve for the parameters, which are usually s and t. We plug those parameter values into the parametric expression for z and see if we get the required value of the z coordinate. Now, more information here about planes. One and only one plane can be determined in any of the following four situations. We're given a line and a point not on the line, all of which are on the plane. We're given three non-collinear points that are all on the plane. What that means is if we're given 3 points that lie in a line like this, that won't be good enough. There has to be non-collinearity to those 3 points. But if that happens, there's enough information there for us to determine the vector equation of a plane. We could have two intersecting lines, both of which that are on the plane. That'll let us know non-parallel intersecting lines. That'll let us have enough information to get a vector and or parametric equations for a plane. And finally, we could have two parallel non-coincident lines. That would also do it. So let's do this. First question is going to be like the second example here. We're going to see how would we come up with the equation of a plane if we were given three non-collinear points, like we are right here. So any three of these points will be our position vectors. So it doesn't matter which one we use. So let's say I use the point 6, 2, 1. And I shouldn't say the point is used as the vector. What I'll say is, if I know the point 6, 2, 1 to be on the plane, then I know the vector 6, 2, 1 can be a position vector. That's a better way of saying it. Now, to get two direction vectors, it's pretty easy. I actually just figure out what is the vector between A and B. And when I do that, I get the vector between A and B is 3, negative 6, 1. Because 9 minus 6 is 3, negative 4 minus 2 is negative 6, and 2 minus 1 is 1. Okay? Then I want to know what's the vector between A and C. And for that, the answer is negative 7, because negative 1 minus 6 is negative 7, negative 2 minus 2 is negative 4, and negative 3 minus 1 is also negative 4. So we have two direction vectors down below. Now, like we said in the previous video, there's a convention in math to make the first non-zero component of a direction vector positive. So if I know that I could use negative 7, negative 4, negative 4 as a direction vector, that means I could use a vector collinear with it as a direction vector instead. So let's just multiply negative 7, negative 4 by negative 1, and we'll get 7, 4, 4. And if we do that, my first my first non-zero component of the second direction vector is positive. My first non-zero component of the first direction vector is positive. I have my position vector from earlier, which I said is the vector 6, 2, 1. And I just pick a parameter s to go in front of the first direction vector and a parameter t to go in front of the second direction vector. And I have what I need. Okay. And then the parametric equations would be 6 plus s times 3 and plus 7 times t. That will be the equal to x. That'll be the equation for x. And a similar process gives us the equation for y. 2 minus 6s plus 4t. And for z, 1 plus s plus 4t. Okay. Now, what if we have a plane with the parametric equations shown, and we want to determine a point where that plane crosses the x-axis? Every point on the x-axis has a y-coordinate and a z-coordinate of 0. So all we're going to do is we're going to set y and z equal to 0. And when you do that, you get two equations with two unknowns right here. Again, letting y and z be 0 there. You see we get two equations with two unknowns. All we'll do is we'll solve for s and t, and assuming we get a solution for s and t, we'll plug those in for x. We'll find out what we get, and we'll have a point. So letting y equals 0 and x equals 0 tells us equation 1 that 2 minus 6s plus 4t equals 0. Equation 2 that 1 plus s plus 4t equals 0. Rearranging equation 2, we would get s equal to negative 1 minus 4t. And plugging that into equation 1, we would ultimately get 28t equal to negative 8, which means t is negative 2 over 7. Okay? Then we take that value and we plug it in, since we now know what t is and we know that s is negative 1 minus 4t, we plug in that value of negative 2/7, and we get that s will equal 1/7. So we now know that when x is 0 and when y is 0, we have a s value of 1/7 and a t value of negative 2/7. We take those values and we plug them into x. And when we do that, we get x equal to 31/7. And remember, y and z are already known to be 0, so the point where the plane intersects the x-axis is the point 31/7, 0, 0. Now, what if we want to determine the vector equation of a plane containing a point 0, -3, -2, and a line r equals 3, -2, 9 plus t 11, 2, -3? Well, we have a position vector and one direction vector, and our position vector is we have a position vector and one direction vector. We need one more non-zero, non-collinear direction vector. Well, since we know the point 0, -3, -2 is on the line, on the plane, and since the point 3, -2, 9 is also on the plane, we know that the vector between those points is on the plane. So the vector between 0, -3, -2 and 3, -2, 9 is the vector 3, 1, 11. So we know the vector 3, 1, 11 is on the plane. But we also know that the vector 11, 2, -3 is on the plane, because if a line is on the plane, then so is that line's direction vector. So we actually have this direction vector of 3, 1, 11 and this direction vector of 11, 2, -3. They're non-collinear. And at this point, we can use either 0, 3, -2, -3, -2, or 3, -2, 9 as our position vector. And we can give our answer. Our position vector is given here. Our first direction vector is given here. Our second direction vector is the vector we found earlier between the 2 points, and that is put here. And we have to make sure we're using different parameters for the 2 different direction vectors, and that's the vector equation of the plane. And I should technically be putting s and t are elements of the reals here, but I forgot there. Now, what if we know that the 2 lines shown are both on a plane? Well, if the 2 lines shown are both on a plane, then both of the direction vectors are on the plane. So we've been hand-delivered both of our direction vectors. And we only need one position vector, but either position vector given would be good. So we pick either one of those 2 position vectors and both direction vectors, and we have an equation of the plane. So we're going to use the position vector of line 1 as our position vector of our plane. And we're going to use, before we go on, that position vector, -5, -13, -1, you might be tempted to say, hey, sir, let's multiply it by -1 and get 5, 13, 1 as our position vector. That would be wrong. That's the sort of thing you can do with direction vectors because you're going infinitely in both directions. You can't do that with position vectors, and that's what's written down at the bottom. We can't multiply a position vector by -1 to make its first component positive because a position vector indicates a position. We can only do that with a direction vector, whether we're dealing with a line or a plane. So we keep our position vector with its negative first component, that's fine. And we keep both of our direction vectors like this, and we have the equation of a plane. And of course, again, I'm forgetting to put s and t must be elements of the reals. Now, we're going to determine an equation of a plane containing these 2 parallel non-coincident lines. See, we know that these lines are parallel because 2, -7, 1 is collinear to -4, 14, -2. It's a scalar multiple. So, we know they're parallel. We don't necessarily know them to be non-coincident. So it's theoretically possible that in this type of question, we might have to show they're non-coincident by showing that the 0.226 is not on the first line. We don't have to do that in this question, though, because it literally tells us they're non-coincident. We take the question at its word. So we're going to be able to use 2, -7, 1 as one of our direction vectors. We can't use -4, 14, -2 as the other direction vector for our plane because those direction vectors have to be non-collinear. So instead, what we're going to do, we're going to use a vector between -370 and 226, or a scalar multiple of it, to be our other direction vector. And then we're going to use either one of those vectors to be our position vector. So we need a position vector, and we can use either -370 or 226. So we'll use -370. We'll use 2, -7, 1 as one of our direction vectors because it's the direction vector of the line. We won't use -4, 14, -2 as the other direction vector because two direction vectors of a plane need to be non-collinear. So we'll find, like we said earlier, the vector between the 2 points. So that vector will be the vector between -370 and 226 is equal to 2 minus -3, which is 5, and 2 minus 7, which is -5, and 6 minus 0. Whoops. 6 minus 0. Which is 6. And so we have our second direction vector. And so we can state that the equation of the plane, as shown at the bottom, is r equals -370 plus s times 2, -7, 1 plus t times 5, -5, 6. And again, I keep forgetting to say that our parameters must be elements of the reals. Now, we're going to determine two lines that lie on this plane. This is definitely a plane because we've got a position vector. There's no parameter in front of that. And we also have two direction vectors and with different parameters in front. So we know that that is definitely a plane, and the direction vectors are non-collinear. So all we have to do now is say one of our lines will be this position vector plus a parameter times that direction vector, and our other line will be this position vector plus a parameter times that direction vector. So that equation contains one position vector and two direction vectors. If we use the position vector in one of the direction vectors, we get the equation of a line. If we use the position vector in the other direction vector, we get the equation of another line. And so the two lines are given as shown.